Improve min/max downsampling. I have some large arrays, 100 million points, that I need to interactively plot. I am currently using Matplotlib. Plotting the arrays as is gets very slow and is a waste since you can't visualize that many points anyway. So I made a minute/max decimation function that I tied to the slim_changed callback of the axis. I went with a minute/max approach because the data contains fast spikes that I do not want to miss by just stepping through the data. There are more wrappers that crop to the x limits and skip processing under certain conditions, but the relevant part is below. This works pretty well and is sufficiently fast. 80 ms on 1 × 10⁸ points and 2k bins. There is very little lag as it periodically recalculates and updates the line's x and y data. However, my only complaint is in the x data. This code duplicates the x value of each bin's left edge and doesn't return the true x location of the y min/max pairs. I typically set the number of bins to double the axis pixel width, so you can't really see the difference because the bins are so small. But I know it's there, and it bugs me. So attempt number 2, which does return the actual x values for every min/max pair. However, it is about 5x slower. This takes roughly 400+ ms on my machine, which becomes pretty noticeable. So my question is basically, is there a way to go faster and provide the same results? The bottleneck is mostly in the numberpy.argmin and numberpy.argmax functions, which are a good bit slower than numberpy.min and numberpy.max. The answer might be to just live with version number 1 since it visually doesn't really matter. Or maybe try to speed it up something like Python, which I have never used. FYI, using Python 3.6.4 on Windows. Example usage would be something like this.
I managed to get an improved performance by using the output of arg, min-max, directly to index the data arrays. This comes at the cost of an extra call to numpy.sort, but the axis to be sorted has only 2 elements, the min/max indices. And the overall array is rather small, number of bins. I checked the timings for your example and I obtained.
So this doesn't address speeding up the specific function in question, but it does show a few ways of plotting a line with a large number of points somewhat effectively. This assumes that the x points are ordered and uniformly, or close to uniformly, sampled. Set up. Here's a function I like that reduces the number of points by randomly choosing one in each interval. It isn't guaranteed to show every peak in the data, but it doesn't have as many problems as directly decimating the data, and is fast. And here's the min and max to see the signal envelope. The following function can take either of these, and uses them to reduce the data being drawn. The number of points actually taken is 5000 by default, which should far exceed a monitor's resolution. Data is cached after it's reduced. Memory may be an issue, especially with large amounts of data, but it shouldn't exceed the amount required by the original signal. Here's some test code. On my machine this displays very quickly. Zooming has a bit of lag, especially when it's by a large amount. Panning has no issues. Using random selection instead of the min and max is quite a bit faster, and only has issues on very high levels of zoom.
Edit, added parallel equals true to number, even faster. I ended up making a hybrid of a single-pass arg-min plus max routine and the improved indexing from @_sensor and linked to this related simultaneous min-max question. This version returns the correct x values for each min/max y pair, and thanks to number is actually a little faster than the fast but not quite correct version. Comparing the speeds using Timite shows the number code is roughly 2.6x faster and providing better results than V1. It is a little over 10x faster than doing NumberPy's argmin and argmax in series.
Did you try PictGraph for interactive plotting? It's more responsive than Matplotlib. One trick I use for downsampling is to use array_split and compute min and max for the splits. The split is done according to the number of samples per pixel of the plot area.
If you want to support the channel, please consider liking and subscribing.